All right, happy Thursday. I hope that if you got the vaccine today, you're not too destroyed by it. And as I said in class yesterday, feel free to not show up. This video is going to be quite long and detailed. And try and see it before you show up for class on Friday. Otherwise, Friday's class is going to seem very strange. And we kind of take a turn here in our learning and do something super cool. It's not that advanced, but might feel that way. And just trust me that it makes life easier once you understand it. So here we go. This is called implicit differentiation. So let's do some. Let's. I'm going to make a note here. Normally I recall stuff from the past, but I'm not sure you've learned this, so I'm going to say, let's just note this. And this is a definition. If f of x is a function of the variable x only, then we say f of x is explicitly defined function. And you're just like, so this is the definition of an explicit function. So, I mean, when I say y equals f of x, I mean, if you write this, x is the input, and for every x you input into the function, you output a y. And so when you graph it, you have something like this. Y equals x squared plus 2x plus 1, which we're defining to be f of x. And so everything over here is either has an x or it's just a constant. Okay? And all the differentiation rules we have learned so far, all of them, chain rule, product rule, quotient rule, power rule, all of them imply that the function you're dealing with is, why is that on? Here we go. Draw the finger off. Okay. I don't want random marks everywhere. So all the functions we've dealt with so far are explicit. We're saying y is the output, x's and constants are the input. And then we can also say, all right, let's look at the graph of this particular explicitly defined function, right? So x is the independent variable that lies on the horizontal axis. If you rewrite this, it's this. So it's got -1, 1. And if you graph it, it's a nice pretty parabola with a vertex at -1, 0 that opens up, right? And I've asked you, I mean, we're on week 6 now. Sorry, yeah, week 6. And I've asked you a million times, oh, let's say x was 0. What's the equation of the tangent line there? Or otherwise, what's the slope? What's the slope of the curve? Y equals f of at x equals 0. And sure enough, you take the derivative, you plug in 1, and you get what, 2, right? So that's the slope of the curve here. It's the slope of the tangent line at this point. Okay. Explicit function. Now, here's where we go slightly astray. Now, let's just say I ask you to graph the curve defined by this equation, x squared plus xy plus y squared equals 1. This is supposed to be in black. I have a whole plan here that I'm not even following. Here. I have a script. Because this is so important. So, black. Graph the curve defined by the equation x squared plus xy plus y squared equals 1, and find the slope of this curve at 0, 1. Okay, so here I'm going to make this an example, sort of a learning example thing. So first we have to graph this curve. You've never learned this, I doubt. I've only taught this to a few people in high school. I've never taught it in Math 100 because it's not part of the curriculum, but nonetheless, via calculus, we'll be able to graph this by the end of term quite easily. And so I'm going to go into purple because it's my favorite color, and I want to just let you know that anything in purple, you don't have to copy. I just want you to follow. Okay? I want you to follow. And so since it's in purple, just follow me for a minute. Don't write. And see if you can sort of hang on, and I'll fix things on the flip. Okay, this is an ellipse, and if you graph it, if I graph it, I should say, at 1, 1, minus 1, minus 1. So all of these points are intersection points on here. If you plug in x equals 0, you get y equals plus or minus 1. And this thing, it's actually symmetric with respect to the line y equals minus x. So this might be the ugliest ellipse I've ever made, but there it is. It's an ellipse. And the question I asked here was what's the equation of this tangent line? Or actually, what's the slope at 0, 1? Okay, well, we don't know how to take the derivative of this because why? Because why? Oh, come here. If you take x squared plus xy plus y squared minus 1, and you call this a function, this is a function of x and y, right? It's not just a function of x, it's a function of x and y. It's got two inputs. And this is calculus of a single variable. There should only be one input. So the question is, can I make this y equals f of x explicitly? Okay. Well, I'm an algebra master. I can say that after 23 years of teaching and a PhD. And so I know how to do this. I can make it. I can make this happen. And I'm going to do it for you here. And again, this is in purple. And that means you're not really responsible for it. So here we go. I'm going to rewrite this as y squared plus xy equals 1 minus x squared. And if you remember completing the square, what you do here is you take half of this x and you square it. So this is x over 2 quantity squared, and you add it to both sides. And then by the magic of completing the square, you get this, which is 1 minus 3x squared over 4. You take the square roots of both sides, which is plus or minus the square root of 1 minus 3x squared over 4. You solve this for y. Found a common denominator inside of there. And now you write it like this. So I have now done it. I have said, okay, now y is a function of x only, because all I have over here are x's and constants. Now, here's where I'm trying to sell you on this implicit differentiation before I've even shown it to you, right? I'm marketing. Okay. I know I'm looking for the slope of the tangent line at the point 1, 0, and that's where sorry, what is it, 0, 1 or 1, 0? I've already lost it. 0, 1, okay. 0, 1. So I have to make a choice here because these are two functions. One of those two functions is this guy, and the other one is this. So already this sucks because you have to make a choice. So we need to choose, and we choose the positive exponential here. Okay. So to find the slope, you need to take the derivative of this. Now stepping into this problem, this derivative, is like stepping onto the fourth ring of hell. Okay? And you know, clearly I know how to do it, but I'm not going to because this is silly, right? This is silly because there's a better way. But, and this drives some people crazy, I can still define this explicitly, this particular curve, even though I shouldn't. I can. Where this 3.7, this whole implicit differentiation, becomes super powerful is here. Let's take another example. Same question. And now I have something like x cubed plus x squared y plus y cubed equals 1. This is a curve. Okay. I use Desmos to graph it. It goes like this. It does a weird funky thing here like this, and then it comes down like that. Okay. And it's logical to ask, A, can I find the derivative? We can. B, can I define this explicitly? And the answer is no, right? This nightmarish thing I did here to find f explicitly isn't even possible. And because of that, you can't use product quotient, any of that stuff, given what we know. So, what do we do? Right? And what we say is that this equation is implicitly defined. In other words, y is some function of x that remains unknown. We actually don't need to find it. All we need to find is what dy dx is, given the curve. And that's where this thing comes into play. So this is what we do here, and this is where I leave the book. So this is key. We're going to use the derivative with respect to x as an operator, right? It operates on terms. So I'm going to take the derivative with respect to x of this curve, which is implicitly defined. I can't solve for y explicitly. Okay? Here's where you need to pay attention. I go term by term because the derivative is additive. So I have the derivative with respect to x of x cubed plus the derivative with respect to x of x squared y plus the derivative with respect to x of y cubed equals the derivative with respect to x of 1. Okay? And let me get some color in here. This one and this one we know how to solve because they're explicitly defined. Okay? So let's just knock those out while we can. By the power rule, this is 3x squared. We don't know how to handle these yet. And by the power rule, the derivative of 1 is 0. Okay. Okay, so here's the crux. We're going to do this one first. Okay, and I'm going to pull it out over here as a subproblem. What's the derivative with respect to x of y cubed? Okay, what we say is we assume y is a function of x. Again, we don't know what it is because we can't solve for y. We just assume it is. And then we use the chain rule, right? So y prime is going to be 3y squared times dy dx. Okay. We did the outside, and then we did the inside. And again, we just don't know what the inside is, so we're calling the derivative of the inside dy dx. So this becomes 3y squared times dy dx. You really need to let that marinate for a second. In the layman's terms, what you do is pretend the x is a y and differentiate it and then slap on a y prime. Right? Okay. Back to the problem. So now we have the 3x squared, which is hanging on from before, plus this derivative, which we haven't computed yet. We've now done this derivative, which is 3y squared times dy dx, and so that equals 0. And now we're going to deal with this guy as a subproblem number 2. Subproblem number 2. Okay, and so we need the product rule. So we're going to fix the y and take the derivative with respect to x of x squared, and then fix the x squared and take the derivative with respect to x of y. All right? So this is y times 2x, and just like before, when you take the derivative with respect to y, you treat y as if it was an x, so you get a 1 times dy dx. Okay. Whew. All right, so now let's put it all together. Back to black. We have 3x squared plus this new guy, 2xy plus x squared times dy dx plus 3y squared times dy dx equals 0. All right. So now we finished doing the differentiation implicitly. Our original answer was to find the slope of the curve, and what we do now is, just like Math 100, solve for dy dx. This is the final step. Okay. All right, so we collect all the terms with dy dx. So we have x squared. I'm going to stick with this color. Plus this equals what's minus 3x squared minus 2xy. And then on the left hand side here we factor out a dy dx. Oh yeah, and now divide by and so that dy dx equals minus 3x squared minus 2xy over x squared plus 3y squared. And that's the derivative. All right, so all the other rules still apply. But every time you get to, think of the dx as an operator, every time, so if you think of ddx as an operator, every time it says, if it sees something with respect to x, it just attacks it, right? If the operator sees this, then it, it attacks it. But the second it sees something with a y in it, it does this. It takes the derivative of this, as if it were an x, times dy dx. You pick that up every time from the chain rule. Right? So if you were finding the derivative with respect to x of e to the 2y, right? This would be 2e to the 2y times dy dx. Right, and all I did was pretend for a second that that was an x, and I differentiated it, and then I slapped on y prime or dy dx. Right, and I'm only using dy dx because I'm using ddx over here. It's even faster, but slightly illegal to go 2e to the 2y times y prime. Right, same but different. All right, let's do a problem here. This is a GP. Hopefully you'll read it, have a go, and then see what I did. So we want to show that the point 2, 4 lies on the curve x cubed plus y cubed minus 9xy equals 0. And then find the tangent line at this point 2, 4. So this is Book's notation. So 1 show, and then 2 show that. So 1, we're just showing the curves on there, right? So let's check, because it wouldn't make any sense if it wasn't. So we have 2 cubed plus 4 cubed minus 9 times 2 times 4. And the question is that equal to 0? Oh, I don't know. This is 8. What's 4 cubed? 2 to the 6, 8 squared, 64 minus 72. And that's 0. So yeah, it's on there. Okay, 2. First of all, we're going to find m tan, the slope of the tangent line, and this is dy dx evaluated at the point 2, 4. So again, we need to find dy dx. Right. Okay, so let's do that. We have, now I'm going to use my ddx operator here. I have the derivative of x cubed plus the derivative of y cubed minus 9 times the derivative of xy, and that's equal to the derivative of 0. Okay. this looks similar to the last problem. So the derivative of, so this is just standard fare, 3x squared. This is 3y squared times y prime, or dy dx, minus 9. Now we're going to take this derivative. So we're going to fix the x and take the derivative of the y, which is 1 times y prime plus y times the derivative of x, which is 1, and that equals 0. Okay. So here we go, 3x squared plus 3y squared y prime minus 9x y prime minus 9y equals 0. And again, all these primes I want to keep in red just to show you where we did the implicit bit. Okay, now we're going to solve for y prime. Okay, so this says now I have 3y squared y prime minus 9x y prime equals 9y minus 3x squared. Again, keeping my y primes in red. Okay. Factor out the y prime here. And then lastly, solve for y prime. Okay, and that's the derivative. Now to find the slope of the tangent line at this point, we need to plug in the point what? 2, 4. So this is what? This is 9 times 4 minus 3 times 2 squared over 3 times 4 squared minus 9 times 2. And what's that? 36 minus 3 times 4 is 12. And then we have 16 times 3 is 48 minus 18. This is 24 over 30, which is 4/5. Right? 6 goes into 24 4 times, 6 goes into 5 times. So this is M10. Okay. So now we're going to use the equation of the line here. So we have y minus 4 equals 4/5 times x minus 2 minus 8/5, and finally y is 4/5 x minus 8/5 plus 4. What the hell is that? 4/5 x plus 12. It's funny, all the calculus was really easy, and now this last step is killing me. 4 times 5 is 20. 20 minus 8 is 12. All right. Man, I hope this works. Okay, let me write this down. 4/5 x plus 12/5, and the point in question is 2, 4. All right. Let's just go over to Desmos and have a look here. I bet it's on here. I think I was playing with this last night. No. Okay. So we have, where's my pencil? We have x cubed plus y cubed minus 9xy equals 0. There it is. It's a super cool curve. All right. 2, 4. Is it on there? It's on there. Okay. Let's label that guy. Okay. So let's see here. Man, if this doesn't work, I don't know what I'm gonna do. All that work. 4/5 x plus 12/5. Oh, there it is. Right. And we found it, just like that. And again, there's no way to solve this curve explicitly for y. So this is the only way to find these slopes and these tangent lines. Okay. If you got this guided practice, apart from graphing it, because we don't know how to graph these by hand, these are really cool curves. They're special. They have a big thing to do with cryptography and Bitcoin. If you've ever heard of Bitcoin, I taught this course in cryptography, and we learned how to graph these. But it's an insane amount of algebra, and it's nothing we need for calculus. Yeah, that was that. I don't have anything else here, so if you come to class, if you're not sick or busy getting vaccines, I'll put together a few more guided practices to do in class, and then we'll clean this up on Friday in the workshop. Okay, hope you enjoyed that as much as I did. I love this stuff, and if you understand this implicit differentiation, related rates, which is the topic we're doing next week, which I'll have to say is generally regarded as the hardest topic of the term for some people, right? Only given 3 days to it. Most people only give 1 or 2 at most, but I've given 3 just because it's important, and I like to move slow. Okay, I'll see you all in a few minutes if I don't